the sine and cos and to the trigonometric functions, we're going to start by going through all of the mother graphs. Okay, so the mother graph is basically the most basic form of the sine, cos, and tangent graphs. Okay, so let's have a look at the sine graph. So the sine graph has this shape. Let me do that. Okay. So this is the shape of the sine graph. So we have two possibilities for the sine graph. We have a positive sine graph and we have a negative sine graph. Okay, so one of the key features, or one of the key elements or distinguishing features of the sine graph that we can remember is that the sine graph always starts at 0. Okay, whether it's positive sine or negative sine graph, it always starts at 0. So this is a regular Cartesian plane. Okay, that with our y-axis and our x-axis. Okay, moving up and down, meaning on our y-axis we measure in singular units. Okay, so 1, -1. So as you can see, the mother graph has 1 and -1. Okay, it can be like 2, 3, 4, whatever. Those changes to the graph, which we'll discuss in a bit. But the mother graph, okay, has units of 1. Okay, so in this case we have 1 and -1. This is the y coordinates on the y-axis. Okay, then we have, okay, so they're slightly different. So for the sine graph particularly, it starts off at, let's use gray. Okay, it starts off at, so the sine graph, its first x coordinate is actually 0 degrees. So it starts off at 0 degrees. Then the next, don't you move in singular units, we move in degrees. Then the next x-intercept of the sine graph, which is over here, this is 180 degrees. Then the next turning point, which is there, this is 270 degrees. And then finally, the final x-intercept of a singular sine graph is at 360 degrees. Okay, so we can see that the total, the highest degree on a sine graph is 300 and you lagging. Your screen is frozen. Okay, sorry. Let me try and fix that. Okay, is my, okay, let me. Okay, tell me as I speak now, is it still the case? Like, am I still lagging? I see that the screen is a bit blurry. Am I still lagging as I speak? Hello, hello, testing 1, 2. It's better. No, it's fine now. Okay. So should I restart everything that I was explaining? Because it was obviously laggy and you guys couldn't hear. I probably am because I didn't explain much. Okay, but just let me know either way. Okay, so just once again, let's sort of restart the lesson. Okay, so we said that we're discussing trigonometric functions. Okay, so we did previously, we did other functions like the parabola function. As soon as it starts lagging, just let me know and I'll try and fix it. Okay. We did parabola functions, we did hyperbola functions, we did exponential functions, and we discussed all of those in detail, all right? Now we're going to do the trigonometric functions. So the trigonometric identities, or the trigonometric ratios that we know are sine, cos, and tangent. So we're going to do the graphs, okay, and the functions for sine, cos, and tan. And we're going to start off with the most important part, not the most important part, but an important point to start off with. And in order, the most important fundamental understanding of this section actually is the mother graphs, okay? And also relating the mother graphs to the different types of graphs that we do get, okay? So like I said, the mother graphs are the most basic form of each of our functions, okay? So we started off with the sine graph, okay? And we have two possibilities for a sine graph, a positive sine graph and a negative sine graph, okay? So just sine x and negative sine x. And we said that this is a regular Cartesian plane. So we have a y and an x axis. On the y-axis, we move in singular units, so 1, 2, 3, 4, okay? The mother graph, however, just has 1 and negative 1, okay? So the sine graph has a maximum value of 1 and a minimum value of negative 1. That actually is the range. You'll see, we'll look at it later. The range of a sine graph is 1 to negative 1, or negative 1 to 1. However, on the x-axis, okay, so our x coordinates, we don't move in singular units, we move in degrees, okay? And we start off at, a property of the sine graph is that it starts off with 0 degrees. Okay, it starts off at 0 degrees, and it moves in intervals of 90. So that's the first thing to notice, is that our sine graph moves in intervals of 90. So here we have x-intercept to turning point 90, then that x-intercept, that turning point to the next x-intercept, another 90. So we move in intervals of 90, the mother graph, to 70 and 360. This is always true for the mother graph. Okay, 100% voice is lagging again. This is terrible. That's really bad, actually. I'm getting it back now. That's terrible. Okay, let's give this one more go. And if I hear another message, then let's see. We'll have to try something else. Okay, let's try this and let's see how it goes. Hopefully it's a bit better. Okay. So I think the part that was lagging was I was just discussing this. Okay, the intervals of the sine graph moving in degrees. Okay, and the intervals. Okay, so we basically refer to it as it's actually called the step of the graph. Okay, and it starts off at 0. And when we talk about the step, it's always from, on the mother graph specifically, it's always from the x-intercept to turning point to x-intercept to turning point to x-intercept. Okay, this is known as the step, and we move in 90 degrees. Okay, 90-degree intervals. So from 0 to 90 to 180 to 270 to 360. Please, if it is lagging again, do tell me. Okay, don't feel shy, even if you told me before. Okay, so 0 to 90 to 180 to 270 to 360. So for the mother graph, this is always true. From x-intercept to turning point to x-intercept to turning point to finally the last x-intercept, we move in steps of 90 degrees. Okay, then we have the final coordinate being 360 degrees. So the total wavelength, right, if you do physics, right, and you remember from like when you discuss waves, this sort of looks like one complete wavelength, right, where we have like a crest and a trough. Okay, the total wavelength, or the total period, this is function, the total period of this graph is 360 degrees. So for one complete sine graph, it takes us 360 degrees to complete it, because we have to go from 0 to 90 to 180 to 270 to 360. Okay, and please note that this graph can be repeated in an infinite amount of times, right? So we can continue it like that and like that to the negative direction. Okay, it continues towards positive infinity as well as negative infinity. Okay, so that's the positive sine graph. Okay, now let us discuss the negative sine graph. Okay, just by the way, is it a bit better now? Is it a bit more consistent? Has there been any issues? Okay, so that's for the positive sine graph, right? So we discussed y values goes to +1 and down to -1, and the x value start at 0 and go to 360 in steps of 90. Okay, perfect. Thank you. Let's hope it stays like that. Okay, and whoever's on YouTube, just confirm for me as well that it's better. Okay. Okay. Cool. Okay, so that's for the positive sine graph. Now let's discuss the negative sine graph. So the difference in the negative sine graph is it actually flips or reflected about the y-axis. So technically, if you compare sine x and negative sine x, so both of these are functions. So we can say y is equal to sine x and y is equal to negative sine x. Okay, if you remember from transformations that we did, the change that was made here was y was made negative, because remember when we make y negative, we essentially make the whole function negative. I'll give you another example. If we have y is equal to x squared plus 2x plus 3. Here, if you want to make y negative or reflect it about the x-axis, in order to make y negative, here you'd make y negative, and then you'd take the negative over to the other side to leave y alone. You'd have y and negative, whatever the entire function is. That's making y negative, or in other words, reflecting it about the x-axis. Okay, so in this case, what actually happens from sine x to negative sine x is that it's reflected about, sorry, not the y-axis, it's reflected about the x-axis. Okay, so that's one way to remember it. Alternatively, you can just remember that this is a wave that starts at 0 but goes up first, and this looks like a wave that starts at 0 but goes down first and then up. Okay, so if you notice, you'll see that all you're making y negative for this interval, all the y values became negative, and here they were negative, and then they became positive on that side. Okay, so the same applies here with regards to the x coordinates. So here we have 0. At this point, we have 90. At this point, we have 180. Here we have 270. These are x coordinates in degrees. And the period of the negative sine x graph is 360 degrees. Okay, so two different mother graphs. One for sine and one for negative sine. Okay, cool. Okay, now let's look at just some formalities, some things that are standard for all graphs. So this is specifically for the mother graph. The period of the mother graph of sine x, okay, these are properties of the sine x mother graph, is 360. That's always the case. And the step is 90. Right now, remember we discussed what the step is. The step, okay, we can describe it as on the mother graph specifically, from x-intercept to turning point and so on, right? So from x-intercept to x turning point, or from x turning point to x-intercept, right? All of these values on the mother graph specifically give us the step of the mother graph, okay? And it's the case for other graphs as well, right? The next thing, so alternatively, what we could also understand it as is the step is basically 1/4 of the graph. So it's like the graph is broken up into 4 different pieces, 4 equal pieces. Okay, so that's what we can understand from the step. Of course, the period is the entire length of one sine graph. Okay, so irrespective of what your actual period is, because the period could change, you'll see later on, 360, 180, 720. But the total length of just one full, if you want to call it a wavelength, that would be your period. Okay, one complete rotation of your sine graph. Then we discuss the range, which is also a constant for the mother graph. Okay, the range is y is an element of -1 to 1. Remember, we discussed how do we do range, and in this case, it's how high and how low the graph goes. So our start value and our end value, essentially our lowest value and our highest value. Lowest value, highest value, and it's inclusive because these values are points on the graph, 1 and -1. That's how we get the range of the mother graph to be y is an element of -1 to 1. In the other notation, it would be y is greater than or equal to -1, but less than or equal to 1. Lowest, highest, both inclusive. Okay, we don't discuss a domain that's covered here. They ask for period generally. Let's move on to the cos graph. Okay, so now with the cos graph, it's the same story. You can see that the range is -1 to 1. So y-axis, we move in singular units, and x-axis, we move in degrees again. So with the x-axis, again, we start at 0 degrees. Then we move on to 90 degrees. So the step for the cos graph is the same. Then we move on to 180, 270, and finally 360. So again, the period of the cos graph is also the same as sine, right? It's 360 degrees. But the difference here is our initial y value is 1. So this is a distinguishing feature. Okay, it differs from the sine graph. How can you remember? Sine graph starts at 0, but cos graph starts at either 1, okay, or -1 for the -1. We'll go through that in a second. But yes, that's how you can differentiate between the two. Sine starts at 0, but cos starts at 1. And then again, turning point to x-intercept, to turning point to x-intercept, to turning point, right? These are, what you call them, steps. This is the step, okay? And a cos graph is technically a sine graph that has been shifted. Because if I continue over there, right? If I continue my graph, and let's just say I start here. Now, okay, it's not like 100% accurate, but if I consider this part of the graph, you can see that that looks like one complete sine graph, okay? So a cos graph is essentially a sine graph that has been shifted to the left by 90 degrees. Okay, that's true, and we'll discuss that like trigonometrically when we do changes. Okay, so this is the cos graph, right? You can remember that this sort of looks like a cup, if you will, and this sort of looks like a mountain. Okay, then let's have a look at our negative. So the difference is that it starts at -1. That's the y value, and the x is 0. Its step is still 90. Okay, mother graph of sine, step is still 90. So this guy is 180. And the next step, which is to the next intercept, is 270. And the last one to the last turning point is 360. So let's look at this. We have the period of the cos graph, the mother cos graph for negative and positive cos x, by the way, is 360. The step is 90, okay? And the range is y is an element of -1 to 1, or y is greater than or equal to -1, but less than or equal to +1. Okay, so that is constant for the mother graph of sine and cos. They have the same period, the same step, the same range. Okay, they're very similar. It's just that cos starts at 1 or -1, while sine starts at 0. And then goes to 1 or -1, depending whether it's positive sine or negative sine, and depending whether it's positive cos or negative cos. Okay, and remember that a cos graph is essentially a sine graph that has been, it's almost as if it's been shifted. It has been shifted 90 degrees to the left. Because if we look at that, right, that would look like a complete sine graph. It's just that this part is now there. Okay. Cool, and you'll see how that will make sense when we talk about it in terms of reduction in a bit. Okay, so let's have a look at this. This is the tan graph. So the tan graph now, the sine and the cos were very similar, but tan is now slightly different. Okay, it differs from the two. The range and the period both change for tan graph. So the tan graph looks like this. Okay, we have these two things. I'll get rid of this and I'll rewrite it. So we have two dotted lines which represent vertical asymptotes. So the tangent graph has two vertical asymptotes. Remember that asymptotes are lines that the graph will never touch. Okay, so maybe get closer and closer and closer and closer and closer and closer forever, as close as possible, right? Close to a small, minute value that we cannot imagine. Okay, but it will get closer and closer and closer, but they will never touch. Okay, that's what is an asymptote line. So our tangent graph, we're going to deal with our positive tangent graph. It looks like this. So we have vertical asymptote number 1 and vertical asymptote number 2 on the mother graph. Okay, and the period, actually, the total, we can call it the total x length, okay, is 180 degrees. So the period of this graph is 180 degrees. You can see that by noticing the distance between the vertical asymptotes from -90 all the way to 90. That's the complete graph. Okay, it's from negative 90 to 90, but not including negative 90 and 90 because they are asymptotes. Okay, so yes, right. So this is the shape of a tangent graph. It's always the mother graph crosses through 0. Okay, always crosses through 0 and 0, crosses through the origin. Okay, here it curves upwards, here it curves downwards. That's the shape of the tangent graph. Positive tan, you start on the top right. Negative tan, you start on the top left. That's how I like to remember it. Okay, and then you just complete the shape. Okay, and the second thing, or we actually discussed it first, but the second thing is the vertical asymptotes, negative 90 and 90. Okay, so the graph never touches those points, and the tangent graph, the mother tangent graph, has these asymptotes. So the distance between them is 180 degrees. So write that a bit neater. 180 degrees, telling us that the domain, okay, we refer to it as the period, is actually 180 degrees as opposed to the 360 for sine and cos. So if you remember for general solution, right? Remember for general solution, for sine and cos, we use plus k times 360, but for tangent, we use plus k times 180. And here's the reason why, because the period of tangent is 180. So now I just want to sort of extend this graph. We can do this. Okay, and just to complete it, right, remember that this graph can go on forever and forever. So if I draw in another one, I would have to draw the next asymptote 180 degrees away from 90. So we can put it there somewhere, and we can say that this is 180 plus 90 is going to be 170, I believe. Sorry, 270. Okay, because plus 90 is 180, plus 90 is 270. So the next vertical asymptote will be at 270. So at the middle of them, between them, at the middle point, that's where the graph is going to cross the x-axis, and this would be 180 degrees. Okay, and we would have to fill in another graph here, and it would look like that, something like that. Okay, so the next asymptote 270 towards the right, and on this side the next asymptote is 180, not 270. So the next asymptote from this side is 180 degrees to the right, and in this side it's 180 degrees to the left. Okay, and that's if you're drawing as many tan graphs as you want. You can possibly draw as many tan graphs as you want. Of course, in questions you'll see they'll restrict it with a certain domain. They won't let you draw on for till infinity, nor will they draw on till infinity. They'll just be a restricted domain. Okay, but just keep that in mind that these graphs can potentially be drawn till infinity. Okay, and that's how it would look. So when I say that this represents the mother graph with a restricted domain of from negative 90 to 90. But if you had to go from negative 90 to 6,000, you'd have to draw all the tangent graphs that fit within that range, considering all of the asymptotes as well. Okay, and the same applies for tan, sine, and cos. Now, let's just quickly look at a negative tangent graph. Negative tangent graph looks like this. Same vertical asymptotes, negative 90 and 90. It's just that we start on top left and on top right, but it passes through the origin. Now, one thing I do want to note that will be able to tell you about vertical shifting of a tangent graph is that you should always note that the midpoint, okay, from the x-intercept here, so this is 0 degrees. Its midpoint between 0 and 90 is 45. Let's use red. It's 45 degrees. The midpoint from 0 to 90 always has the y coordinate 1, provided that there is no vertical shifting. Okay, which there, yeah, okay. Provided that there's no vertical shifting, the midpoint from the x-intercept of the tangent graph to the asymptote always has the y coordinate 1 or negative 1, because we have to consider this one as well, this midpoint. Okay, this would be negative 1 and negative 45. It's the midpoint between 0 and negative 90. It's negative 45, and it would have the corresponding y coordinate of negative 1. Okay, provided that this graph has no vertical shifting, so it hasn't been shifted up or down. Because if it has been shifted up, then that changes it, of course. In that case, it would be different. Okay, so just keep that in mind. That's the positive tangent graph, negative tangent graph discussed with their asymptotes as well. So to take note, we have that the period of a tangent graph, the mother tangent graph, is 180 degrees, and its range is y is an element of real numbers, because this goes forever up and forever down. So it has y is an element of real numbers. That includes positive infinity to negative infinity. Okay, so that's the sine, cos, and tan graphs. Now we're going to look at we can call them transformation, I'll heading this again later, transformation or changes to the graph. Okay, now transformation, what we need to note is these are specifically changes, okay, to the mother graph. Okay, and I noticed teaching students and following this that when we reference our changes to the mother graph, okay, it's always easier to understand what happens. Okay, so always understand that these changes, you treat them as changes to the mother graph. So you have this memorized. You need to know how your sine graph looks. You need to know the period, step, and range of your sine mother graph. You need to know how your cos graphs look. Okay, positive and negative for all of them. You need to know the period, step, range for your cos graph. You need to know how your tangent mother graph looks. You need to know period and range. Okay, by the way, tangent graph has no step. Okay, you need to know all of that in your head, and these transformations need to then be, again, changes to what you know about the mother graph. So you just basically need to know your mother graph well, which I'm sure most of you do already. Excuse me. And then when we talk about transformations, again, these are changes to this mother graph. So I want you to picture it in your head that when we make these changes, you are going to think of the change being made to the mother graph above. So the first change that we're going to make is, if you remember from transformations, right? We had f of x where there's two different ones, right? F of x plus 2, we had f of x plus 2, okay? We had negative f of x. Okay, I don't think we're going to have that here necessarily, but it's fine. Okay, we discussed these four different types of transformations. So this, if you remember correctly, is a change to y. Okay, it's a change to y, and if it's plus, it's up, and if it's minus, it's down, right? The y coordinates follow logic because plus means up, minus means down. However, this guy here is a change to x values because it's within the bracket, it's with the x values, but this is attached to y because remember, f of x can be represented as y. So it's the same thing as saying y plus 2. Now, if you're going to add 2 to y, that means you're changing y. That's how we can understand that f of x plus 2 on the outside is a change to y. Okay, so that's why we know it's either up or down, because when you change y, it's up or down. Right? And now when it's inside of the bracket, that's when it's what? That's when it's a change to x, where it's opposite to logic, where plus means to the left and minus means to the right. Okay, it's opposite to logic in the equation. Remember, in the actual graph, we follow logic, but in the equation, it's opposite to how we would normally think. Right? And then this here we said was reflect about, so you're making y negative, so that means reflect on the x-axis. Okay, make all the y values negative. Then we talk about this guy, okay, f of negative x. Oops. Okay, so this is just a recap of what we discussed on transformations in the regular functions that we've done. Okay, and here this is a reflection, okay, about the y-axis whenever we make x negative, right? And it's we considering making all the x values negative. Okay, so this is just a quick recap of the transformations that we learned in normal functions. Now let's have a look at this. Okay, what I want you to remember is that your sine x, okay, your sine x is essentially, it is just a function. So your equation, it's just like a normal parabola function. This could have an equation. So you'd have y is equal to, firstly, sine x. This is the equation for this graph. Y is equal to sine x. Alternatively, f of x. We could represent it by f of x. F of x is equal to sine x. The function of x, how do you want to get the x coordinate? You take the sine of that x. Okay, y is equal to f of x is equal to sine x. This is representing the equation, right? It is a function, just like parabola, just like exponential, just like hyperbola. This is a trigonometric function represented by the equation sine x. So now for all of these, essentially we have y is equal to sine x, or f of x is equal to sine x. So sine x plus 2, we can clearly see plus or minus 2. We can clearly see that this is a change to y, okay, because it's making a change to x. It's not inside the bracket, okay? So this is a change to y, where if it's plus, it's up, and if it's minus, it's down. So in this case, it's plus 2, so we're shifting 2 units up, or it's minus 2, we're shifting 2 units down. Let's have a look at the next one. This is sine x plus 2 or sine x minus 2. This is within the bracket, so this is a change to x, which in the equation works opposite to logic. Negative or minus means to the right, plus means to the left, right? So these are very similar to your regular functions transformations, just now with trig functions. Okay, so far these two very familiar because we've done them in regular functions. Okay, one is the change to y attached to the outside, and one is a change to x, which can be found inside of the bracket. Okay, one follows logic, the other does not. Now, let's have a look at the two that we don't necessarily deal with in regular functions, and that's multiplying. Okay, so we can either, as you can see, the difference between these two, this 2 is multiplying the entire function, so it's multiplying y, but this 2 is multiplying the x value. Now, remember, this is a trigonometric ratio, which has sine and an angle. Sine. And what do we put inside of sine? We put an angle. Okay, for example, sine theta. Okay, or sine x. That's the same thing, right? But that represents the angle. So when you take a 2 and you multiply it by the angle inside, okay, or whatever this this x value is, you multiply it essentially by x. It differs to when we multiply the 2 outside as a coefficient. Okay, so that's the difference between the top one, the third one, and the fourth one. Okay, so keep in mind when we multiply the angle, this creates a change to the period. Okay, so remember I said that the period of the mother graph we discussed, those don't change. Like, for example, the period of the sine mother graph is 360. So how does that get altered? How does the period change? So the period changes essentially by doing this, by multiplying, putting a coefficient to the angle of our function. So in this case, what the change is, what the coefficient is 2. So x is multiplied by 2. Whatever the coefficient is of the angle, we take the original mother period graph. Let's create some space. Okay, this is the, what is this? Period of original. I don't even know if there should be another I, maybe not, of original sine mother graph. Okay, so the period of the original sine mother graph, and we divide it by what? Okay, we divide it by the coefficient. We divide it by the coefficient of the angle itself. Okay, and please remember, we discussed what is the angle. When I'm talking about the angle, I'm talking about the value that goes, if you had to put sine in your calculator, the value that goes inside of that bracket. Okay, that x value. Whatever the coefficient is, sometimes if you have, for example, sine x over 2, in this case, the coefficient would be half, because this could be re-represented with sine a half x. Okay, so you always have to try and get it expressed in terms of a coefficient. So this would be sine a half x. Okay, and in that case, the coefficient would be half. So in order to find what this calculation is actually helping us to get is the new period. So for the new graph, because I'll tell you in 1 second, this is the new period. Okay, because we're trying to relate, remember I said we try to relate everything to the mother graph. Sine 2x is not the same as sine x. Okay, so we know that sine x has a period of 360, but we don't know what is the period of sine 2x. Okay, so that's why we relate it to the mother graph to determine the period. That's essentially what we do. So basically, what you also need to remember, more importantly, when you have a better understanding, is that this is a change to period. So whenever we have, for example, instead of sine x, we have sine 2x, so a change to this angle. This is a change to period. Okay, and since it's a change to period, we need to calculate the new period. You take the period of the old original sine mother graph, which is 360, and you divide it by the coefficient of the angle. You take the period of the original sine mother graph and you divide it by the coefficient of the angle. In this case, the coefficient of our angle is 2. So we're going to divide it by 2, and that gives us essentially the new period. So the new period in this case is 360 divided by 2, which is 180 degrees. Okay, so the coefficient of the angle changes period. If you want to calculate the new period, okay, period is like domain essentially. Okay, you take the old mother graph, you divide it by that coefficient. Now, similarly, the step, right? So remember, the step is essentially quarter of the graph, and it takes from x-intercept to turning point, x-intercept to turning point, and so on. So what the first thing we can do is we can take the old step. So this guy here. What is this? This is the old step. And divide it by the same thing, right? The coefficient, copy the coefficient of the angle. You could do that also. So the first thing you did was you took the old period, divided it by the coefficient of the angle, that gave you the new period. If you want new step, you take the old step divided by the coefficient of the angle. New step. So this helps us to get the new step. Okay, and in this case, we would get 90 divided by 2. That would give us 45. That's how we calculate the new period. Okay, there's another way to calculate the new period. Since the old period can be calculated by taking the entire thing and dividing it by 4, because remember, it is at the end of the day a quarter of the graph. So what we can do is take our new period that we got 180 and also divide it by 4, and that would give us 45 as well. Okay, so 2 ways of doing it. First way, I showed you. Second way, by taking the new period and dividing it by 4 as well. Always 4, because that's what the step is. It's a quarter of the graph. Let's discuss the next change, which is a coefficient of the function. This is sine x. It's a trigonometric function. Y is equal to sine x. And we're going to compare it to y is equal to 2 sine x. Okay, so this, again, we're going to relate it to the mother graph to try and understand the change that y is equal to 2 sine x does to the sine x function. Okay, and what we should note and memorize is that it's always a change to amplitude. It changes amplitude. Essentially, it changes the max and the minimum value. That's maybe a better way to understand it, because I don't think they specifically always refer to amplitude, but I think when they teach it, then they always just say change to amplitude, change to amplitude. But you must remember specifically the definition of amplitude is the length between the rest position and the maximum, okay? And this is not always that number. The distance or the units between the rest and the maximum is not always this number. Okay, so I'll just teach you how to remember it. It's better, but you can remember change to amplitude because essentially that's what it changes. All right. Now it's firstly, it's okay. So it's a change to amplitude, which is also a change to the max and min. Okay, so we multiply the max and min by what? By the coefficient. Okay, but now I'm not going to say coefficient of the angle. I'm going to say the coefficient of the function. Okay, the entire thing, because that's what affects amplitude. The coefficient of the function, this of the y value essentially. Okay, so multiply the max and the min by the coefficient of the phi or the coefficient of the function. So the old maximum, we should memorize this, that the maximum of the mother graph is 1. The minimum of the mother graph is -1. So multiply the old max and min. So again, we're relating it to the mother graph. Okay, multiplied by what? Multiplied by the coefficient of the function. This is going to give us the new max and min. Let's use the correct color. Okay, this is going to give us the new max and min. Okay, so multiply this by what? By 2, of course, because that's what's in front. Let's change this to a 3. Okay, just so it's different to the previous one. And we multiply this by 3. And multiply this by 3. So the new maximum is 3. And the new minimum is -3. So I hope you understand why I was saying that it doesn't necessarily give us the new amplitude. It does, but more specifically, it gives us a new maximum and a new minimum. And that's the change that we should actually make to the graph. When you see a 3 in front, it means, okay, you need to change what? You need to change the max and the min. You need to multiply the max and the min by 3 and -3. Okay. So yes, that's in simple terms, that's the transformation of trigonometric functions discussed. Okay, please, if you have any questions, please do ask. I see that the stream seems to be fine now because I don't think anyone has mentioned. Okay, so let's have a look at this entire function. So remember, the most basic function we can have is f of x is equal to, and of course, we're just working with sine x, with cos x and tan x, all of these would apply, by the way. I just gave the example in terms of sine x, but with cos x and tan x, all of the same things would apply, right? The 2's in front of the angle or in front of the function, changing it inside the bracket, outside the bracket, they would have the same effect on those graphs. So since we're working with sine graph, I made this. So the most basic sine graph is f of x, is equal to sine x. Okay, let's call it g of x. G of x is equal to sine x, right? This fg doesn't matter. It's just a variable that we can choose anything to represent it. Just the most common is f of x. So we can represent any function as the most basic form, the most basic form of a trigonometric function, with a bunch of changes, and just depict what change they make, okay, and how to remember it. So here we have 2 sine x. So the number in front, let's do this maybe. There we go. The number in front, that changes and that affects the maximum and minimum value. Then we have the number in front of the angle. So look at this one carefully, right? The thing in brackets is the angle, and this is the number in front of the angle. And you'll see I'll discuss something more specific with regards to that as well. So that affects the period always. Then we have this guy, which is a value added or subtracted to the x value within the bracket. That is a left or right change, basically. And in this case, this represents 5 units to the left. Then finally, we have this guy, which is the, actually, this I should highlight with the plus. Okay, this here is outside the bracket, the green one that we're discussing. It's outside the bracket. Okay, so this is a change to y, which is 1 up or 1 down. So here are these changes placed in one entire function. So this is how you need to be able to identify them. Okay, immediately that is a change to max and min or amplitude. This is a change to the period because it's a coefficient of the angle. Okay, and this is a change to x. It's an addition or subtraction to x, so that's moving left or right. And this is a change to y because it's outside the bracket, so it's moving up or down. Okay, so that's just all those changes identified. Now, one thing you need to note is that if you have something like 2 sine 3x plus 60. Okay, if I had to, changes were made to sine x, okay, to obtain 2 sine 3x plus 60. Okay, so remember, yeah, we discussed like this changes max to min, period, 5 left, 5 right, whatever. All right, so I just want to see what are your answers. So the first one is one change is that I'd shift 60 degrees to the left. So 60 to the left. So the direction is correct because it's plus, right? So 60 degrees to the left. Okay, what is the next one? Someone tell me. Okay, we'll end on this, by the way, and we'll leave like a few minutes open for questions, and then we'll end it. So we'll end it here. When we continue next time, we'll discuss the changes in range. Okay, we'll try and do this graph of the changes that we discussed there. Okay, and then we'll continue with application of trig. So obviously in this lesson, we didn't have time to continue with that. So we'll do application of trig and we'll do a question for each. Okay, but yeah. So we have, okay, amplitude is 2. So max and min is 2 and -2. So it is a change to amplitude, correct. So this one represents a change to amplitude. So there's a new max and a new min. So the new max, this is easier to think. So you see the reason why I don't like to talk about amplitude, I'll quickly just mention it here, is because of this one reason, right? So let's just say we have sine x, okay? We have this nice, cute little sine x graph. And now we want to draw sine 2x. So I'll show you actually how sine 2x looks. So sine 2x will start at the same place, but it will go up to 2 and it will go down to -2. So it would look something like this. Have the same x-intercept, but to -2. So here, this would go up to 1 and -1, but sine 2x would go up to 2 and it'll go all the way down to -2. So this would be represented by, sorry, not sine 2x, that would be represented by 2 sine x. Okay, now, if we have to just use the understanding that the amplitude is from rest to maximum, the coefficient change represented the amplitude. So the first amplitude was 1. When we made that 2, the amplitude became 2 sine x, but that changes. What if we have to draw 2 sine x plus 1? Now it's 2 sine x, so it's this pink graph, but now it's essentially shifted 2 units up. Sorry, 1 unit up. So it would look actually something like every single coordinate would shift 1 unit up. So it would look actually something like this. Okay, now in this case, from rest to the amplitude is actually going to be 3. Okay, but this represents 2 sine x plus 1. So this doesn't always represent amplitude specifically, that 2. Okay, I hope you guys understood it. It's a bit of a rough diagram, but essentially that's why that number, the coefficient, doesn't always represent the amplitude specifically, but rather we can understand that it multiplies the max and the min, okay, by that number. So even in this case, even though the coefficient is 2, the maximum is 3. That's because of vertical shifting, moving up or down. So moving up or down could change that, okay? But we make that change first. We initially multiply the amplitude like how we did in the pink graph. Then we can shift it 1 unit up to get the green graph. Then we can determine max and min, okay? But for now, we're just dealing with this, okay? Max is going to be 2 and min is going to be -2. This one is easier because you can see that there's no vertical shift. So we know for sure that the max is going to be 2 and the min is going to be -2, just by the way, okay? Then we have the step is 30, the period is 120, the period will become 120. So that is indeed correct because we take old period 360 and we divide it by 3 to get the new period of 120. Perfect. So we've identified the 3 changes. Okay. The first one is a horizontal shift. The second one is an amplitude change or max and min change. And the third one is a period change. Okay. So one of them is actually incorrect and its value is incorrect. I'm going to tell you which one it is. It's this one here. This, guys, is technically incorrect. The direction is correct, but this 60 is incorrect. And I'm going to show you why in a second. So what you should always do, okay, you should always take out the common factor within the bracket. Always do that. Okay. So 2 sine, the common factor we can take out there is 3. X plus, now we say 60 divided by 3, x plus 20. Always take out the common factor because what this is a representation of the angle when the 3 is multiplied inside. Okay, but if you look at it in its previous form, okay, what had happened was 2 different separate changes were made. Firstly, the graph was shifted, as you can see now, 20 degrees to the left, and it was then the period was changed by a factor of 3. We divide the period by 3. So these are the 2 separate changes made. But this representation basically multiplied that 3 out in the bracket and got it as that. That's why you have to always work backwards to take out the common factor. It's kind of like a bit of a trick, right? You won't actually see it that often because it's quite tricky. Okay, but I'm just teaching it to you just in case. Okay, always take out that common factor. So keep that in mind. So now we can see it for what it is. This is a 20-degree shift to the left, okay? And these 2 remain the same. The max became 2 and -2, and the period changed to 120. You can see that coefficient is generally going to be the common factor that we can take, and the period still remains 3 because now you can see that this represents the angle and this represents the coefficient of the angle. Okay, so always take that common factor. Okay, so that's the part that I just wanted to note. Just this little change here. Please keep note of this little change. Okay, always take the common factor. This is not correct. You'll see you'll get marked incorrect. It's not, it didn't shift 60 degrees to the left. The reason for that is we must always look out for taking the common factor, and you'll actually see that it shifted 20 degrees to the left.